Good morning, Kristen. Let me know when I can start.
Yep, you can start. We hear you great.
Okay, thank you so much for the opportunity to be part of the Globe IOP webinar series. It is an honor for me to share a little bit of what I do with this great team. And I'm an oceanographer. I was born in Puerto Rico. And I study the ocean not in the very traditional way. I actually study the ocean from space. You'll see some of my pictures, even that I study from space. I do sometimes go to the field, collect water like you all did during the IOP. And sometimes I do just water quality, just with water. And sometimes I bring some fancy instruments that I'll probably show some pictures later on. So to start with, let's talk a little bit about what's water quality. A basic definition from like Wikipedia will say that water quality is just a term used to characterize a water body based on its properties, chemical, biological, and physical properties. That's a very broad definition. And different researchers and scientists and program managers will define this slightly different, usually depending on their end user. For example, if it's public health, they'll define it by the amount of bacteria or coliforms in the water. For me, I will define it with water clarity or transparency. But in general, we use several parameters like dissolved oxygen, salinity and temperature, pH, nutrients, turbidity, suspended sediments, and chlorophyll. A combination of those give you a better idea of what's the water quality or the state of a water body. It could be a lake, a river, or the ocean. So a combination of those, like you did during the IOP, the collecting some of those parameters, will give you an idea of how healthy is the ecosystem, if it's polluted, if the water is safe to drink. So it's basically an indicator of the healthiness of the ecosystem in terms of public health or in terms of the ecosystem as itself, as the biodiversity, how healthy it is, and how it's producing. There's many ways to characterize this. Some of the ways that I often use, and I'll talk a little bit, just because I studied from space, so I study a lot of the optics of the water. And one of the basic instruments that we use for water quality is a Secchi disc. And I believe you're all familiar with it because it's in the protocols. And that's the first instrument that you'll see is a little white and black disc. And that tells us a little bit how clear is the water. And the one in the bottom is a fancy one to do kind of the same thing, except it gives us a little more information. And it tells how much light is coming in the water and how much light is attenuated in the water column. And that gives us an idea of the amount of particles in the water. However, turbidity itself is only one of the descriptors for water quality. So usually you need other parameters to better describe the water body. Next one. So just a basic overview. So a healthy ecosystem has a balance of photosynthesis and respiration. It has a diverse community of organisms and benthos, and has normal levels of oxygen and light can go through. So submerged aquatic vegetation can thrive. If we have an influx of nutrients that could be from a point or non-point source, by that I mean, for example, a river will be a non-point that is bringing nutrients, or a facility that works with agriculture nearby, it's have an input of nutrients that can, that influx of nutrients will provide nutrients for a phytoplankton bloom, which in some cases is very important. But if the input of nutrients is too much and the phytoplankton bloom gets to be large, next one. So you can go on this one's a little faster. So yeah, so the phytoplankton bloom, when it goes there, it will create, basically, it will prevent the light to go through. And when it prevents the light to go through, it will start affecting the systems in the bottom, like seagrasses that need the light. And at the same time, when phytoplankton start decaying, and microbial decomposition will start, it's gonna reduce the amount of oxygen in the water. And that usually leads to something that you may have heard of hypoxia, or dead zones, like in the Gulf of Mexico. That is usually pretty bad because it will cause a population decline, loss of vegetation, will also change the chemistry of the sediments, will cause erosion and population decline. And at the end, we classify the system as an unhealthy system. I think we can go to the ocean color one now. So for me to study this in space, it's quite interesting because if the water quality is associated with an input of nutrients and phytoplankton increase and particles in the water, usually the color of the ocean, in my case, I'm studying the ocean, but this applies to rivers or lakes, will change. And you'll see that we always think the ocean is blue, right? But actually, there's many shades of colors in the ocean. It can go from blue in very deep waters with very little amount of particles like phytoplankton or sediment. But as we move to coastal waters, you start seeing more greenish water. Greenish means there's more phytoplankton or little cells that photosynthesize. And if you are nearby a river, you're start gonna get some sediment or color dissolved organic matter. Usually comes in rivers. The very dark photo there, that's a phytoplankton bloom. Believe it or not, that's a Carenia brevis bloom in the Gulf of Mexico. And sometimes it can extend for kilometers, and it can cause a lot of damage, health, public issues, damage to population like dolphins and turtles. And the one that looks like dark patches, those are oil spills, which can also affect the water quality and the healthiness of the ecosystem. The pinkish one is a foam, it's a phytoplankton bloom too that causes this foam. And the last one, lightly greenish, is sargassum. So you'll see that it changed a lot. And those changes, I can actually see them from space. And that's why we can study a little bit of water quality from space. Next one. So based on the color, the satellite will see it as a full spectrum. So it will give you a curve of how the water looks. So the blue one, it means there's more reflectance of blue light. And the satellite will capture that whole curve. And we can actually start seeing difference if we look from different colors. So if you go to the, my right will be the more turbid water, brownish water, you'll see that it looks more reddish in the spectrum. And the spectrum goes from 300, which is purple light, towards 600, which is more red light. And this is the visible part of the spectrum, the part that you can see. That's what I usually use for to study water quality. So based on those differences, we can actually start defining what's in the water. And we can, from satellite, start deciding if there's phytoplankton, if there's sediment, high amounts or low amounts. So it gives us an idea of the water clarity and what's in the water and what could be causing serious issues to the community. And I'll talk more later on. Next one. So this is just a little example of how the satellite works. For ocean color, no, this is not all satellite remote sensing. For ocean colors, we use the visible part of the spectrum. It's a passive satellite. So we need the sunlight. So we'll only have images during the day and days that are free of clouds. But it gives us a global space. So we can see it, we can see the entire globe every day, which is very neat. If you go sampling, you'll only cover a small area. But the satellite allows you to see a larger area and almost every day if there's no clouds. Sometimes you won't have images as much as we want, but at least it provides you a better resolution in terms of space and time. And but the field work that you do is really important because what we see from space, we need to validate. So we receive a signal, which is that spectrum that you see. And then from there, we start defining what's in the water. If there's phytoplankton, detritus, which means fecal pellet, dead phytoplankton, and other minerals. Gelf stuff, which is the color dissolved organic matter, usually is a yellowish substance that come from rivers. And then the water itself has its own properties. So we have to, what we receive from the satellite, we start dividing and trying to define the mystery, what's in the water. That's basically our job. And the job of the community is to help us validate what we see and help improve the development of algorithms to better detect and better determine what's the water quality, or if there's something else like phytoplankton blooms, oil spills, and that kind of stuff. Next one.
I'm going to take a pause and try to share the slides again. I've heard from a couple of people that they're blurry, so I'm not sure if it's because of the, let me try this again. Is that better?
I can see them. They're not as high quality as the one that I can see on my computer.
Yeah, I think it's because they're PDF. I'll try to.
Yeah.
It's better now.
Okay, thank you.
Okay, we can go to the next one.
Okay.
And if I'm running out of time, please let me know.
Okay.
So this is an example of a satellite image. And you'll see we selected little boxes in the image so you can see what the satellite actually measure. So we see the color, but in the back of the color, we have numbers, and those numbers can be translated in a spectrum. And you'll see that depending where we are in those little different shades of blue and green, you'll see that the spectrum does change a lot. And that's what we actually use to determine or create algorithms to define harmful algal blooms or phytoplankton blooms from healthy or not healthy or harmful, and sediments in the water, turbidity. So those are the numbers that we actually use for the different algorithms. Next one. And yeah, the letters are a little blurry. I can share something better with you later on. So these are some examples, and you'll think that there are several algorithms for water quality itself, but water quality itself is also defined by others as it's different things that can harm the public or that can cause problems with the water quality. And one of the main issues that we have nowadays are phytoplankton blooms or cyanobacteria blooms. And those ones are seen usually in very nice greenish from space, and we can have algorithms to detect them. This is a neat program. It's called Cyan. It's a cyanobacteria assessment network, and they use satellite imagery, and they have an app where public can go and collect data and see where they are and see what the satellite sees. And it actually provides data for validation of what the satellite is observing, and at the same time provides a public a service. So this is an example of how water quality can be affected, usually for in cyanobacteria blooms or phytoplankton. Next one. I especially look at harmful algal blooms from space caused by phytoplankton. This one is Carenia brevis. It's a common harmful algal bloom in the Gulf of Mexico. It can last months, and it can stand for thousands and thousands of kilometers. And you can see that the organism that causes it is microscopic. And then it causes large mortality that we can see in the beach. It changed the water to be dark and like a black water. And we can see it from space, and we can actually study how often they happen. We have data for the past 20 years, so we can actually look at the frequency, the dynamics of these phytoplankton blooms. Next one. Yeah, this is a beautiful image from NASA Ocean Color. You can actually find images like this for free at the NASA Ocean Color webpage if you go to the gallery. This is sediment. When the tide comes in, steer the sediment in the Solway Firth, and that's somewhere between Scotland and England. And you'll see that brownish water. You can also see a more darker water if you go inside the river. Those are the turbines. You can see how high the concentration of sediment is. And you can see how it extends into the ocean and how it mixes with the ocean. Next one. This a beautiful image was taken after the Hurricane Durian, and that's the east coast of United States. And if you focus between Florida, North Carolina, and the Bahamas, you'll see that nice turquoise, bluish colors, and those are part of the suspended sediments that the resuspension of sediments after the hurricane. So you can see how it extends all the way, hundreds of kilometers from the East Coast. And so it kind of it gives us an idea of how water quality changes after specific events like hurricanes. And that's very, very important. It's something that sometimes we cannot see if we just go sampling. So the satellite gives us a better perspective of some of the changes in the water quality. You can go to the next one. So the next one is a little bit of work that I did in the Mesoamerican Barrier Reef. And we use imagery to characterize how rivers are connected to some of the reefs in the Mesoamerican Barrier Reef. If you look at the greenish color, this is a chlorophyll image. So it means there's more phytoplankton in the water. And you'll see the greenish waters going all the way from Honduras all the way to Belize. And the one on the left is just a normal day, and the one on the right is after a hurricane. So we actually look at 15 years, I believe, of imagery, and we characterize how many times the reefs are impacted by local rivers from Honduras or Belize, and how far these plumes of particles, which could be phytoplankton and other small other particles like sediment, reach the reef in that area. And it shows us how connected we are in terms of the ocean doesn't have barriers. So things that are happening in Honduras can affect reef in Belize, and the same goes around the globe. And next one. So the last slide is just an example of how citizen science can be used to create algorithms from space. This data was collected by the actual retired Maryland State Senator, Bernie Fowler. He went to the same area in the Patuxent River in Chesapeake Bay, east coast of United States. He went since 1988 with his white sneaker or shoes, put them in the water, and measure the depth that he can stop seeing those shoes. So basically, it's like the Secchi disc. So he goes in the water, and he stops where he doesn't see the shoes anymore and take the depth. That can be converted to the turbidity in the water. And we had an intern that actually used all that data, converted it, and created an algorithm for water clarity in the Chesapeake Bay. And that's the image that you see on the other side. So this is a good example of how important the citizen data is and how useful it can be to use for interpretation of the satellite imagery that can be used globally. And I think I'll stop there. Thank you so much. If you have any questions.